6.3 is binomial and geometric random variables. So we are now going to take our foray into binomial random variables, okay? Binomial random variables. A binomial random variable or binomial is where you have one or the other. It's either heads or tails, it's even or an odd number, or it's a success or a failure. It can be, several different things. You can be, it doesn't have to be 50% chance, right? It can be I roll a dice and I either roll a 1 or I roll something else, right? This would be binary, right? Because you're either going to roll a 1 or you're not going to roll a 1. In other words, if you define probability of rolling a 1, a success, your success would be this, right? So your failure would be what? It'll be 1 minus that, right? With the other times when you don't roll a 1, right? Every other time, anytime when you don't roll a 1, you can either roll a 2, 4, 5, 6, 2, 3, 4, 5, 6. 5, right? So 5 out of 6, okay? All right. So what's always going to happen here is that your success plus a failure is always going to equal 1, okay? Because it's one or the other. There is no other choice, okay? So that's what we call a binomial situation, okay? That's what we call a binomial situation. So let's go to page 404. And we have a definition there, definition of a binomial setting, okay? This comes up in the AP test quite often. They're gonna ask you if you are in a binomial situation or not. So if you're in a binomial situation, the pneumatics that you're gonna remember is bins, okay? So it's going to be binary, it has to be binary, okay? Has to be independent. Each throw or each whatever you're going to do is going to be independent from one or the other, right? Okay. And then N, the number of trials, N, number of trials is preset. In other words, we know before we start how many times we're going to do this. Okay. And then you have S, and where S means the same probability. So the probability that you use on throw 1 is the same as throw 10, is the same as throw 20. Okay, the same probability all the way through. Okay, so these are the 4 things that you have to check for to make sure it is actually a binomial situation. Okay, so let's read the example there on page 405 and see if each one of these are binomial or not. A, genetics says that the genes children receive from their parent are independent from one child to another. Each child of a particular set of parents has a probability of 0.25 of having type O blood. Suppose these parents have 5 children. Count the number of children with type O blood. Okay, are we binary here? So we're either going to have type O blood or we're not, right? So it's a success or failure there, right? Independent, or each child independent. Yes, it is, right? It says right up front, right? It says they're independent from one child to another, right? Number of trials is preset. What are the number of trials here? Can anyone tell me what the number of trials are? Kayla.
5, because there's
5.
5
You have
kids.
5 kids, right? You have 5 children, right? Okay. The same probability, the probability to have O, the 0.25, is the same all the way through. Okay. All right. So yes, indeed, A is a binomial situation. B, shuffle a center deck of 52 playing cards, turn over the first 10 cards, one at a time. Record the number of aces you observe. Okay. So, is it binary? Yeah, it's binary, right? It's going to be either ace or not, right? You're going to have an ace or not, right? Okay. Are the number of trials preset? Yeah, you have 10 of them, right? Are they the same probability? No, they are not, because every time when you open one up, whether or not you have an ace, changes the probability. In other words, also by the same token, they're not independent, right? Because of that, because there's no replacement. Okay. C, shuffle a deck of cards, turn over the top card, put the card back in the deck, shuffle again, repeat this process until you get an ace. Count the number of cards you had to turn over. Okay, so what's the problem with this? Ace is either you're an ace or not, so it's binary, right? Is it independent? It's independent because you're looking at it and then you're putting it back in and you're shuffling again, right? Number of trials is preset. Is this preset? I don't think so, right? The numbers is not preset, right? Because there's no defined how many trials I'm going to use, right? I could get the ace right off the bat, just like that, and I'll have just the trials will be one. Okay, you could, there's a possibility you would do it 50 times and you wouldn't get an ace. Okay, so they're all different. Okay, so that's why this one will not be a binary situation. Okay. So that's what the bins is about. Okay. Flip the page, go to 406. Definition of a binomial random variable, binomial distribution. The count of successes x in a binomial setting is a binomial random variable. Okay. The possible values of x are 0 to n if you do n trials, right? If you have n trials. Okay. The probability distribution of x is a binomial distribution. Any binomial distribution is completely specified by two numbers, the number of trials and the probability of success, right? So you're gonna have n and p. So the number of trials and the probability are the two things. If I know those two things, my binomial distribution is set, right? N is the number of trials, and then it's an R, trials, and then P is the probability of success, right? The probability of success. Okay, so let's see how we calculate a binomial probability. Okay, how we calculate a success in a binomial situation. So those of you who've done calculus should understand this. This is basically, it is the probability of me succeeding, right? So where are we at? So let's go to page 407. The definition of a binomial coefficient is we have n r, right, is equal to the same as this, which is n factorial over what? N minus r factorial, correct? Okay, we've done this before, right? We've done this before. So 10, 2. So if I choose 2, if I have 2 successes out of the 10 tries, right? 2 successes out of the 10 tries, okay? And let's say so this will be what? This is just the 10 choose 2. So this will be 10 factorial over 10 minus 2 is 8 factorial, 2 factorial, right? So what do I get? I get 10 times 9 times 8, 7, 6, 5, 4, 3, 2, 1. And 8 factorial is 8, 7, 6, 5, 4, 3, 2, 1. And 2 factorial is 2 times 1, right? So 8 all the way through this cancels out with this. So I have 9 times 8 times 9, 10 times 9 here divided by 2, which is going to be 45. Okay, so that would be my coefficient. That would be the coefficient. Okay, but that alone does not give me the probability of success, right? What do I have to multiply on top of this? I have to multiply the probability of, I'm going to have, I don't know what the probability is, but we'll find that out later. Okay, so we'll do that on, if you flip the page on page 408. Okay. Well, before that, there's a technology center. It just tells you that this operation is doable on your calculator. Okay. You use math, I think it was math prob, right? Go to math and go prob, and then it'll give you the n choose R situation. Okay. So if you want to look at the actual probability formula, the probability formula is, if I'm going to get R successes out of n trials, okay, so if this is the probability of success, right? The rest of the time I failed, so it'll be that, right? If this is the chance of failure, right? This is the chance of success, and I have R successes, and then I have this many failures. The rest are going to be failures. Okay, so this would be the probability of solution. Okay, now if you think about it, let's say that I'm going to roll the dice 5 times. Okay, and we're going to define, we're going to say if I choose 2, okay, if I choose 2, and I'm going to roll the dice, and we're going to say rolling 1 is a success, then this was the success. I had 2 successes, and the rest I failed, right? Out of the 5 times, the rest I failed, okay? So basically what this is doing is this. This part is easy here. This part here is easy because, yes, I succeeded twice, I failed 3 times, okay? This merely designates which I'm going to do first. Okay, so how many different ways can I put so success, failure, success, failure, success. No, we're going to have actually 2 successes here, right? So it's going to be, can I go like that? Can I go like this? Can I go like this? Okay, this is merely that. This is I'm going to have 2 different successes out of the 5, okay? So this is what this is determining here, and this is the probability stuff over here, okay? So you can view it that way. Maybe that way it'll be easier to understand, okay? So let's go to page 409 and put this all together and see if we can actually do some work with it, okay? So let's go to example number, we're on 409, the top one. It says, Jeanette says that the genes children receive from their parents are independent from one another. Each child of the parents has a probability of 0.25 of type O blood. Suppose we have 5, and we're gonna have 5 children, that X be the number of, and find probability of X equals 3. So find the probability that we have 3 kids that have the type O blood type, okay? So basically the blood type success was 0.25. I'm gonna have 3 of these, right? And we're gonna have 5 trials, we have 5 kids. So the rest are failures. In other words, they're not O's, right? So we'll have 2 of those, and we're gonna have to fit the 3 different kids in certain order, right? So this is just ordering them, okay? So 5 factorial, over here I'm gonna have 3 factorial, 2 factorial, right? Because it's 3 and then 5 minus 3. Then here I'm gonna have 0.25, I'm gonna have 0.75 squared, or another way to do this would be 1/4. This would be 3/4, right? So I have 5, 4, 3, 2, 1, 3, 2, 1, 2, 1. So this cancels out. The 2 in here cancel out. I have 10 here. So 10 different ways to order this. Times 4 to the third 1, 4 to the second, and I'm going to have 9 here. Everyone understand where the 9 comes from? The 9 here is 3 squared, right? So I'm going to have 10 times 9, 4 to the 5th, 90, 4 to the 5th, whatever that may be. Okay? So that's how you would calculate that. Okay, let's go to the next one. It says the preceding example tells us that each child of a particular set of parents has a probability of 0.25 having type O blood. Suppose these parents have 5 children. Should the parents be surprised if more than 3 of their children have type O blood? Okay, so that'll be what? If I want to have more than 3, so the probability of me having more than 3 is what? Probability of x being greater than 3 is basically the probability of x equals to 4 and the probability of x equals to 5. Those are the only 2 choices you have to have more than 3. So let's look at the 4. The 4 would be this. Again, 0.25, 4 successes, 1 failure. Then we're going to add to that this guy, 5, 5, 0.25 to the 5th, 0.75 to the 0, because I have no failures. They are all O. Okay. This is going to be 5 factorial over 4 factorial, 1 factorial, times 0.25 to the 4th, 0.75, plus 5 factorial over 5 factorial, 0 factorial, 0.25 to the 5th. This guy is 1, because it's to the 0 power, right? This is always going to be 1. Okay, so here's a couple of things here. So 5 factorial over 4 factorial will be what? This should be 5, right? Because this is 5 times 4 times 3 times 2 times 1. This is 4 times 3 times 3 times 1. So anything below the 5 cancels out. All I've left is 5. So this becomes 5. Okay. 0 factorial is 1. So this is 1. 5 factorial divided by 5 factorial is 1. So this is basically 1. So this is basically what you're left up with. And if you do this out, you get a grand total of 0.01563. So the probability of me having either 4 or 5 kids that have O blood type is 1.5%. So if that happens, should I be surprised? Yeah, I should be surprised, because it only happens 1.563% of the time. Okay? All right, so let's flip the page. And it tells you how to calculate binomial PDF and binomial CDF. Okay? Binomial CDF and PDF. Okay? All right, so let's go to page. So let's go to the first one, binomial PDF, okay? So binomial PDF is the first one we did. The first one we did, it was the one where we calculated actually x equal p, x equals 3, right? It was probability of x equals 3, and that is by, what was it? Binom PDF, because that's a single when it's 3, right? And we were going to do 5 trials, 0.25 success, NP3, okay? So this is what you'll put into your calculator. The other one, the next one is the one we just did, right? So we binomial. What am I trying to find? I'm trying to find in the binomial distribution, okay, where it is greater than 3. So what I'm looking for is I'm going to calculate from 0 all the way to 3. And then I'm going to subtract that from 1 is what we're doing here, okay? So that'll be binomial CDF. And I'm going to go NP all the way from 0 up to 3, okay? Notice there's no discussion about negative or anything like that because there is no such thing as a negative success, number of successes, right? Okay. So this is going to be basically the success rate of 1, 2, and 3 added together. It's all the way up to 3. Because what I'm really interested in is what is 4 and 5, right? So I'm going to find this and subtract it from 1. So if I do this, I get 0.98 something, 0.98374,375. I'm going to subtract this from 1 to get the 0.015, whatever we got last time, right? 625. Everybody understand that? Everybody understand why I'm subtracting that from 1? Okay. All right, so that's how that goes. All right, so let's go to page 411. There's a green box there. It says, how to find binomial probabilities. Step 1, state the distribution and the values of interest. Okay, so in other words, find N, find P. That's what you're trying to find, okay? And then perform the calculations and just do what we're doing here, okay? All right, and we're gonna skip that one and okay, we're done. So let's go ahead and take a 5-minute break. Let's go ahead and take a 5-minute break and we'll come back.